Okay, so here's where we were last time. We were talking about section 5.3, and oh yeah, question.
Is that the answer?
Yeah. So, quick reminder: this is the answer to the quiz question.
It doesn't work.
It doesn't.
No.
Really?
It's actually the wrong answer.
Oh, okay. All right. Well, I apologize. Let me.
Wait.
Did it work for anybody else? Oh, okay, good. Oh, great. Okay, all right. I'm glad whenever it's not my fault. Okay. Okay. So yeah. So while we're here, let's go ahead and remember. Don't forget to fill in that code there for attendance. Okay. So in section 5.3, we're going to start a new idea here, which is different things that you can do with this construction that we talked about a long time ago. This goes all the way back to chapter 2, I guess it is, 2.4, defining coordinates of a vector relative to a basis. So the idea is that if you can write some vector in a vector space as a linear combination of basis vectors, whatever coefficients you use are called the coordinates of the vector. So the vector coordinates with respect to a basis are those coefficients. All right, so one way to think about this is that these two statements say the same thing. You know, V is a linear combination of the basis vectors. This is saying the exact same thing. It's just a sort of a different notation to represent that exact same thing. And we read it differently. Here we would say the coordinates of V with respect to the basis are these numbers. Okay. All right, but whenever you see this statement right here, whenever you see this line, this notation, you have to remember what that's telling you. That's telling you that that vector is a linear combination of the basis vectors using those coordinates as coefficients. Okay, so that's all flashback. That's all reminder from chapter 2. I want to think of this in a kind of a different way. I want to think of this now as alternative interpretation of what a basis is. We've thought of a basis as being a collection of vectors, and it is, and that's, yeah, absolutely, that's an important point of view. Two different points of view I'm going to give you now that are different. One is you can think of a basis as being a function. Now, we've certainly not thought of a basis in that way before. But the idea is if you have a vector, right, then pick a basis and the result is a list of coordinates. So you give me a vector, out comes a list of numbers, right? And in general, anything that you have where something goes in, something goes out, that's a function. So this is again, new point of view. We're going to think of a basis now as kind of a function. Okay, and by the way, this goes both ways. Now, I'm going to use the book's notation here to represent, given a vector, what are the coordinates of that vector with respect to that basis? There you go. This is the notation that the book uses. Vector is the input, coordinates are the output. But we know that this relation goes both ways. In other words, we have a uniqueness of representation. For any vector, there's a unique list of coordinates. And of course, obviously, for any list of coordinates, for any list of coefficients, that produces a unique vector. So we have a perfect pairing here. So I don't have to think of this function as a one-way deal. So an alternate way to think of this, an alternate notation, if you have a list of coordinates, you can think of the basis as producing then this vector. And again, it means the exact same thing above. It means, take these basis vectors, use the coordinates as coefficients in a linear combination of those basis vectors, and out comes the vector in the vector space that these coordinates represent. So anyway, think of it in either direction. The book does not use this notation right here. They don't have any notation to represent this going the other way. I made this choice to sort of complement the book's choice here. Going to the right, they make the basis a subscript on the right, which is fine. Going to the left, I chose to make the basis a subscript on the left. Seems like a reasonable complementary sort of choice. Okay. All right. There's a few places where this ends up being convenient, so I like to have it down. Yeah.
When you're proving that this is a linear transformation,
Yeah.
does the basis have to be a set of the same vector space?
Well, sure. Yeah. So if you're talking about a basis for the vector space V, the basis consists of a bunch of vectors that, yes, are in the vector space. Because remember, what we're doing with those vectors is we're producing vectors in the vector space by taking linear combinations of those basis vectors, so they ought to be in the vector space too. Yeah. Yep.
But so if you're adding two of the linear transformations, then they have to be in the same vector space, right? They have to both be in V, right?
Say again? I'm sorry. Okay, let's talk after class. Yeah, sure, I'm sure we'll be able to straighten it out. Yeah. Okay. Okay. So now here's a different way that you can think about this. Oh, so great question, by the way, that calls attention. I almost forgot to mention this note. I would like for you all to take as a practice problem that both of these functions are linear transformations. It's a nice exercise. Again, you know how to check something's a linear transformation. Put a linear combination in. Make sure you get the appropriate linear combination out. Just observe that works here. Yes?
If you read the bracket subscript on the right as the vector B with respect to the basis squiggly B.
Yep.
How do you read your left-hand subscript thing?
Oh, I guess I would say this is the vector whose squiggly B coordinates are these numbers. Yeah.
Okay.
Yeah.
In B.
Yeah. Exactly. Yeah. Okay, so here's a different point of view. Now, this is just semantical. I find this really convenient. I also find this very sort of psychologically satisfying. So you might not like this. But anyway, I'm going to be using the following language a little bit. And that is different point of view on what a basis is here. It itself is kind of like a language. Now, let me sort of talk through that. What do we do with a basis as we have it expressed here? Well, we have this vector space, you see, and in this vector space there's a bunch of vectors, and who knows what kind of weirdos these might be, right? We've seen a lot of oddball vector spaces. The vector space of smooth functions, the vector space of solutions to some differential equation. There's all sorts of strange, non-familiar kinds of vector spaces. So these are things that are kind of hard to talk about individually. And what does a basis do? It takes one of these hard to talk about things and it associates to it a list of numbers. What a convenient, right, familiar, relatable, convenient's a really good word there, by the way. Convenient label to put on one of these things that would otherwise be hard to describe. But if you think about it, that's what a language is, right? So if every time I wanted to talk about one of these things, if I had to draw a picture of it, right, that would be very inconvenient, right? So it's nice for me to just put a label on this thing, and I label it with the word desk, right? And so desk is a convenient, relatable, easy to write down representation of what by itself in reality is a hard thing to talk about. So anyway, I think that metaphor is actually pretty good. Now, quick observation. Notice that if you were to use a different basis here, let's see, let me do it like this. Suppose I were to use a different basis instead of the V basis. Suppose I were to use some other basis like W. Well, it would still be the case that for every vector in the vector space, different basis, if I want to write a vector in that vector space as a linear combination of these other basis vectors, well, of course, I'd get entirely different coordinates. Sure, right? let's say this in the metaphor of languages. One of these things here, which, in English I might describe with the word desk, in a different language I would describe differently. Right? Pick a different language, there's a different word to represent what, of course, is still the same thing. Right? So the language metaphor is actually really good. Right? Anyway, I'm going to be using this little metaphor a lot. I'll be talking about, for example, an alternative way to describe this is I might say, let's represent the vector v in the language of the script v basis. Right? And so when you hear that, when you see that, you should interpret, okay, he means coordinates of that vector with respect to that basis. Okay, very convenient and common. Okay, so a couple of examples. Start with this. Okay, so here's a vector space. All right, the vector space of all polynomials of degree less than or equal to 2. We know that's a vector space, easy to show. I suppose it's not that bad that every time I need to represent an element of this vector space, I could just write out the formula for it. Not that bad. But just because we can, let's talk about how would we represent vectors in this vector space with respect to a given basis. And here's the basis I want to use. The basis consists of these three vectors that I'm calling V1, V2, and V3. Now, I pulled that out of thin air, whatever. It's just an arbitrary random basis that I'm going to choose to work with. So how would I represent some given vector? Let's say this one, F. So there is a vector in our vector space. How would I represent that with respect to this basis? Or, using the other metaphor, how would I represent this vector in the language of the script v basis? Okay, so we recall representing a vector with respect to a basis means figure out how to write it as a linear combination of those basis vectors, whatever the coefficients are in that linear combination. Those are the coordinates of the vector with respect to that basis. Okay, so F is it's a function, it's an element of a vector space. This wasn't even a particularly weird vector space, but anyway, F is a vector in a vector space, but F's coordinates with respect to the basis, list of numbers, element of R3. Said differently, the F may be a function, right? But in the language of this basis, we describe it with a list of numbers. Okay. All right. Now, so a question comes up: how did I find these numbers? Well, that's a system of equations, right? I'm going to write out this right here: expand V1, V2, and V3 as given above. Write F as it's given above. Equate like coefficients. You get a system of equations, and then solve. Right, so that part of the problem is just mechanics, but what I wanted to focus on here is what does this notation mean? Okay, now of course we can also just as well say this function is the 3, 3, 11 linear combination of those basis vectors. So these two statements are morally equivalent. You might say one is like active voice and the other is passive voice, something like that. I mean, they're saying the same thing and just slightly different. I mean, all the same participants with the same punchline, just sort of in a different order. Okay, here's another example. This next example is a little harder. Specifically, this next example is a little bit more confusing. At a glance, it'll look like this question should be easier because look at the vector space we're going to be dealing with. The vector space we're going to be dealing with is itself just R3. Oh, it's our good old familiar R3. That's the least weird vector space we ever have to deal with, right? So I claim that actually makes this a harder problem because what's going to happen is the vectors that we want to represent with coordinates and the coordinates that we use to represent them look the same, right? They're ordered trios of numbers. And so this example is a little bit more confusing just for sort of, you don't get the visual cues of, wait a minute, this is obviously a polynomial and therefore a vector. This other thing is an ordered triple and therefore coordinates, right? So there's no obvious cues like that. So here you have to be a little bit more careful in keeping track of what is what. So here we go. R3, that's a vector sitting inside of R3. Here's the arbitrary basis that I'm picking. Notice I'm writing here my given vector in the vector space as a linear combination of the basis vectors. Again, there's a row reduction to actually find these coordinates. Y'all can do that on your own. Here's what those coordinates are. And they end up being 4, -2, and 1. And so, having written this vector in terms of the basis with those coordinates, I say that this vector's coordinates with respect to that basis are those numbers. Or vice versa, that vector is the 4, -2, 1 linear combination of those basis vectors. Okay, everybody on board? And structurally, this is identical to the last example. It's just weirder looking because of the notational sort of coincidence. Okay. Yep. Yeah, so that's a sort of a chapter 1 problem. So you've got to take you're going to take this, write it out in coordinates, and then you're going to take these, write them out in coordinates, and what you have is an equation that has x squared terms and x terms and constant terms, and then you equate the like powers of x, and there you go. Yeah. So the punchline is you reduce it to a system of equations, and there's a row reduction involved. Yeah. Okay. All right. Okay, so it turns out you can do something very similar with linear transformations. Now, what do I mean by very similar? Let's go back over here for a moment. Here's our point of view on bases. We have this new idea that we're going to use a basis as a shorthand, as a language for representing what would otherwise be, hard to represent. I mean, a vector in a vector space. You take a weird vector space, it could be clunky, unwieldy to represent vectors. So, by way of the basis, we're going to have a compact, convenient, familiar, consistent notation to represent it. Right? So, you can think of a basis as being a convenient as providing a convenient notation for representing vectors, for representing these abstractions. Okay, so that's what we're going to reproduce here. Linear transformations are also abstractions, right? We've seen some weird ones. Linear transformations of, a linear transformation acting on the collection of continuous function defined by, multiplied by some function g and then take an integral from a to b. I mean, some weird thing like that, right? So, can I represent such things with lists of numbers? Is a basis going to help me with that in some form? And the answer is absolutely. So here's how that works. We're going to make a little diagram here. So we've got a linear transformation here, t, from v to w. Let me represent that on our little diagram I want to build. And we're going to pick a couple of bases here. So I've got vectors in this vector space V. I would like to be able to represent them conveniently. And so I'm going to pick a basis that I'm going to call script V. But here's the thing. I'm also going to be dealing with vectors in this other vector space, W, the target, right? I mean, looking at this linear transformation, the vectors that come out are vectors of W. I would like to be able to represent them conveniently. So I have to pick another basis, W, with respect to which to represent those vectors. Okay. All right. Now, y'all have already, I've already suggested as an exercise for y'all to confirm that that's a linear transformation and that's a linear transformation. By assumption, that's a linear transformation. So altogether then, this composition is a linear transformation, right? Compositions of linear transformations are linear transformations. So what I have here then is, in fact, this is a linear transformation from Rn to Rm. And the very first theorem that we proved, first page of section 5.3, first thing that we did on Friday, in fact, was we proved that if you have a linear transformation from Rn to Rm, you can represent that with a matrix. So here's our situation again. Vector representing with respect to a basis. Output vectors representing those with respect to a basis. Then given a linear transformation, T, there is a corresponding matrix, A. And we call this the matrix of that linear transformation with respect to, now you'll notice two bases, right? In order to be able to define this matrix, in order to be able to get this as a linear transformation in the first place, I need a basis in the domain. I also need a basis in the target. Okay, so the linear transformation, this abstract thing that you want to represent, right? You've got to indicate then what basis are you going to use for the input vectors, and then what basis are you going to use for the output vectors. Oh, whoops. Right, and all together then, that defines this matrix. All right, now how do we find such a matrix? What does it mean to have a matrix representing a linear transformation? What does this do? How do I interpret this? Right, we got a lot to talk about here. This is just setup and notation, and now we need to talk about how to make sense out of this. Okay. All right. So, first observation. The matrix, we think of that as being a representation of the linear transformation. So it's kind of, again, almost back to the language metaphor. Once you've picked the bases, then the abstraction of the linear transformation is represented with this array of numbers, namely the matrix. Okay, so it has that same feature that we noticed with vectors. Right, that we have, it's kind of like a convenient label. They create convenient labels that we can put on things. It's like a language. Okay, now how does that? How do you sort of get something down on the page about that? Here's my first example along those lines. Here's a true fact about this matrix, and this is very intimidating to look at. I feel like the first time you see this equation, it's like, oh my gosh, look at all the subscripts and superscripts and curly letters, and it's easy to get lost in what's going on here. So I want to take a minute and walk through what this is saying, which is ultimately not very much. Okay, so here we go. So this won't all fit on the page at the same time, but let me just go through one step at a time. Let's talk about the left-hand side here. The left-hand side of this equation says, all right, I'm going to take a vector v. I'm going to apply the linear transformation t to it. Whatever the result is, I want its coordinates with respect to w. Okay, so take a vector v. We're going to apply the linear transformation and then write the coordinates with respect to w. A vector in the vector space V. Apply the linear transformation and then write the coordinates with respect to W. We're just going over and down in that diagram. All right, now what about on the other side here? What does all of this represent? Well, okay, so let's again sort of talk through it. What's going on here? What does this right-hand side do to V? This says we're going to take V. We're going to first write its coordinates with respect to the script V basis, and then those coordinates I'm going to multiply by this matrix, this TVW matrix. Okay, so coordinates with respect to V multiplied by the matrix. Which is that? Right, so really all this equation is saying, it's like I say, it's not really that big a deal. This equation is just saying that in this diagram, over and down is the same as down and over. It's pretty disappointing. And really, that's just a way of, more or less, of observing that this matrix represents the linear transformation. Right? If you take a vector, if you convert the input vector into coordinates, then what the matrix does is equivalent to applying the linear transformation, with the understanding that once you've done the linear transformation, you convert into coordinates. So with the understanding that as needed, you're converting between coordinates and vectors, with that understanding, what this statement is saying is that A is doing the same thing as T, just in coordinate notation instead of an abstract notation. Yeah.
So, following that diagram, if A were inverted, you could go backwards on the blue arrow. Would that then mean that you could go backwards on the green arrow, like that T would be bijective if A is invertible?
Sure.
So,
Sure. Yeah, that's totally fine. Yeah, absolutely. Yep. Yeah. Okay. All right. Let's get an example down. Here's my first example. Here's a linear transformation. Now again, we'll take a moment to realize this as a linear transformation. So this is the linear transformation of differentiation. This is the act of differentiation. If you give me a at most cubic polynomial, when you take the derivative, like so, the result will, of course, be an at most quadratic polynomial. Okay, so that's what that function is. We've already shown that this is a linear transformation back in 5.1. And what I'm going to do now is I'm going to show you how a matrix represents it in this case. Now, I'm going to pull this rabbit out of a hat. I'm going to just write down what the matrix is. I'll show you where it came from in a few minutes. For the moment, I just want to show you how it is that the matrix is representing the linear transformation. Okay. All right. So we've got to pick a couple of bases. Keep in mind, in our domain, we need a basis. Whoops. Let me. Yeah. Okay. So here. Come on. Here we have a basis for the domain. Easily confirmed. Right? Now I do have to make a choice. You might say this is a sort of canonical choice. This is the easy choice of a basis in P3, but that doesn't matter. All I need is any basis, and it's easy to confirm this is a basis. All right, here's a basis for the target. Right? X squared to x and 1. Again, it's an easy one. Okay, so having picked these bases, said differently, in the language implied by these bases, how do I represent the act of differentiation? Okay, well, I claim that, again, with this basis in the domain, with this basis for the target, I claim that this is the matrix that represents differentiation, which, again, very counterintuitive. It doesn't feel like that a matrix could represent differentiation. Why did we learn all those weird rules back in Calc 1? Why did we learn a product rule and a quotient rule and all that weirdness? I can just multiply by a matrix, right? Well, two things. First of all, you'll notice here I'm restricting our differentiation just to at most cubic polynomials. That's way too limited for Calc 1, right? Also, we have chosen arbitrarily a couple of bases. All right. Okay, so I claim that this is the matrix that works. Oh, by the way, real quick comment. Do be very careful with how you represent the bases. Notice that whatever is a basis for the domain is a subscript here, right? Whatever is a basis for the target is a superscript. That's non-negotiable. That's the notation we're going to use in Math 216. It's the book's choice. I'm very happy with this choice for myself. Let me confess, different books make different choices, and that's fine. But for the purposes of Math 216, we're going with this. Right? Domain is a subscript. Target basis is a superscript. Okay. All right. So I claim that this basically does differentiation. Let's see that in action. This isn't a proof. This is just a sanity check. We're going to consider this vector in P3, and we're going to do the two different things. On the one hand, we're going to take the derivative and then write the result in W language. And on the other hand, we're going to write it in V language and then multiply by this candidate matrix that we allege represents the active differentiation. Okay, so let's just do it. Again, this is just a matter of kind of plug and chug. Let's take this vector, take a derivative, and then write in terms of W. Don't forget what W is. W is the basis x squared, x, and 1. Okay, so we take a derivative. No big. Write this in terms of x squared, x, and 1. Well, now we've got to think about what that means. That means we're going to write this as something times x squared plus something times x plus something times 1, right? So coordinates are coefficients in the linear combination of the basis vectors. And it's not hard to persuade yourself that those are the coordinates that do that. Right? Everybody happy with this? Take a derivative, write coordinates with respect to W with these numbers. Okay. Now let's go the other way. Let's take this vector again, and let's write its coordinates with respect to V and then multiply by the matrix. Okay, just going to follow the rules here. This vector, x squared plus x, when I write its coordinates with respect to V, notice what the V basis is. And again, you got to stick with your choice of basis. Once you've made a choice of basis, you got to stick with it. So our basis here is x cubed, x squared, x, and 1. How do I write x squared plus x as, well, something x cubed plus something x squared plus something x plus something 1. What are these what are these coefficients? Well, again, you look at the vector, right? This vector is clearly 0, 1, 1, 0, right? X squared plus x. So the coordinates with respect to V are these numbers 0, 1, 1, 0. Like so. And now multiply by the matrix, and we get 0, 2, 1. Now let's go over to the other page just to remind ourselves what this matrix is, and let's do that multiplication. We're going to multiply this matrix on the other page by 0, 1, 1, 0. Right, so I'm going to multiply here, 0, 1, 1, 0. Multiply that out. And let's do the arithmetic, and it's 0, 2, 1. Just like over here. All right, so this, it's kind of amazing how this has worked if you really think about it. What's happened here is, okay, sure, we're understanding functions in terms of coordinates. We've got some bases picked, and whether we're in the domain or the target, context appropriate. Yeah, understand vectors as lists of numbers. Sure. That said, the act of differentiation was accomplished by multiplying by a matrix. So this matrix is a convenient, right, familiar, compact label. It's a way of describing the otherwise abstract, imponderable, right, the action of differentiation as applied in these vector spaces. So that's, I think, quite surprising. Okay, yes?
So how did you get the original matrix?
Exactly. Now, that's a wonderful question. She asked, how did I get the original matrix? For the moment, I pulled it out of a hat, and I will pull back the curtain on that trick coming up pretty soon here. Yeah. Okay. In fact, is it right now? Yeah, it's right now. Yeah. I forgot. Okay. So, how do we find the matrix? I pulled that rabbit out of a hat on the last page, but you can't just expect to do that every time, right? So here's the idea. It's a straightforward process, really. Here's my picture, right? I've got a linear transformation. I want to represent it with this matrix with respect to, chosen bases. All right. How do we understand a matrix? Big trick. Columns are images of standard basis vectors. Right, that's one of our big results in understanding matrices from last time, right? From the first page of the lecture notes in 5.3, right? The section right now. If you want to understand a matrix, its columns are the images of the standard basis vectors. So I'm just going to literally write that down here. If you want to understand the columns of the matrix, multiply by standard basis vectors. Okay, what does that look like? We're going to take EI, we're going to multiply by that matrix. And my first observation here is just to take advantage of the fact that that should be the same as this. Right? Going across should be the same as up and over and down. And again, remember, the idea there is that, the matrix is supposed to be doing what the linear transformation T does. With the understanding that you've got to translate from, coordinates to vectors as appropriate. So, by definition, really, of this matrix, the matrix is the same as up and over and down. And now that up and over and down, here's a standard basis vector EI. And notice, up. So write the vector that's represented by EI in the vector space V. Do the linear transformation. And then write the result with respect to W coordinates. All right, so that up and over and down on the diagram, it's just this right here. Now again, this is kind of clunky and, oh my gosh, what am I supposed to do with it? How does this give me an answer? Well, this will simplify actually very nicely. As follows. Let's look at this right here. This says take this linear combination of those basis vectors. And don't forget, we know what these numbers are. When we write EI, that means a list of mostly zeros with a 1 in the ith position. That's what this is. Right, so we're going to take these basis vectors. Hang on. We're going to take these basis vectors, V1, etc., and then there's a VI in here, and then through Vn. Those are the basis vectors I'm taking a linear combination of, and the coordinates, namely the coefficients in that linear combination, all zeros, except for a 1 in the ith position. So 0 there, 0 there. Mostly, I mean, 0's everywhere except for, well, a 1 right there. So this vector, this linear combination of the v vectors, using EI as our coefficients, is just VI. So, like I say, that simplifies really nicely. That is just VI. And this actually is in fact, a very convenient formula for how to compute the matrix, and we'll do an example in just a moment. Let me before I go on to to an example and ways to think about this. Does anybody have any questions about this calculation? Yeah.
So would you find the columns individually one by
I'm sorry, a little louder, please. I'm sorry.
Would you find the columns one by one?
Yeah, that's right. One at a time. Yeah. So each column you compute by executing this formula once. Yep. Okay. We'll see an example momentarily. Okay. So let me tell you how I remember this formula. This is just for my own personal memory purposes. So if you want to find this matrix, recognize you're going to get it one column at a time. And here's the idea. You're going to take these vectors, you're going to put them into the linear transformation, right? And whatever comes out, you're going to write with respect to that basis. Right? I'm taking the V's, doing T to them, writing the results in W language. So my little, again, visual memory tool is you're going to take these, you're going to stick them into there, whatever comes out, you're going to write in that language. Okay, so let's see an example. So recall that previous example we were looking at. We had, D was the act of differentiation. We were applying this to, from P3 to P2. We had bases picked out for the domain and the target. And so here we go. The input basis vectors. Let's go back to where we were. Yeah, here we go. Okay, so wanting to write down this matrix. Step 1, we're going to take these vectors. V1, V2, V3, V4. Okay, x cubed, x squared, x, and 1. We're going to take those input basis vectors. We're going to do that to them. So we're going to take the derivatives of those input basis vectors. And having taken those derivatives, we're going to write them in W language. We're going to write those derivatives as linear combinations of x squared, x, and 1. And having done that to each of the 4 input vectors, that will produce the 4 columns of my matrix. So let's see that in action. Our 4 input vectors. V1, V2, V3, V4. There they are. X cubed, x squared, x, and 1. We're taking the derivative of each of those vectors. Well, those are easy derivatives to take, right? I mean, so the derivative of x cubed is 3x squared. The derivative of x squared is 2x. The derivative of x is 1. The derivative of 1 is 0. Right, so 4 input basis vectors. We apply the linear transformation. We're just taking derivatives. And having taken those derivatives, we now need to write these results in coordinates with respect to W. Okay, so we have to write each of these things as, see, how are these linear combinations of x squared, x, and 1? How are these linear combinations of W1, W2, W3? Well, 3x squared, x squared was W1, so that's 3W1 plus 0W2 plus 0W3. How do I write 2x? Well, keep in mind 2x. I mean, x is W2. How do I write that in terms of W1, W2, and W3. Well, that's 0 W1 plus 2 W2, which you can see right there, plus 0 W3, etc. on down the line. Notice the freebie, 0, always has coordinates 0. That's free and easy. Okay. All right, and notice these 4 columns. Those are exactly the 4 columns of the matrix that I pulled out of a hat when we saw this example the first time around previously. Yep.
So, will this generalize to polynomials like you can?
This is for any linear transformation from any domain with a finite basis to any target with a finite basis.
So, like specifically for polynomial differentiation, could you?
This is just then only for, as we've written it down here, this only works for polynomials in P3, and furthermore, only with polynomials in P3 understood with respect to that basis. Right? And then with outputs specifically understood only, strictly with respect to that other basis.
So, just looking at the pattern though, if you had, say, the x to the 4th coordinate, and you made that bigger by having another 4 up in the top left, it looks like you could just keep scaling this thing depending on what you want to go.
I mean, maybe. Let's talk about that after class. That's a very narrow question. So I don't want to dare try to figure that out in my head, off the top of my head. But the process that we would apply would be same structure as what we're applying here. Yeah.
And you multiply them to get the compose function. These make.
Yes.
We already did.
Composing. Yeah, that's right. We talked about that before. We did. But good observation. Yes.
If you start them in a different order, like
Great question. Yeah. So you're reordering the basis?
Yeah.
Yeah. So if you reorder the bases, then then everything changes. If you reorder the input basis here, keep in mind the input basis vectors give you columns. Right? So if you reorder the input basis vectors, you're going to correspondingly reorder the columns. Likewise, these output basis vectors within a given column, those correspond to the individual coordinates. Well, in fact, then they correspond to rows. So when you shuffle the output basis vectors, you're effectively going to shuffle rows. Yeah, totally. So you do have to be careful about that. You can't just kind of write them down in whatever order you feel like. You got to pick an order and stick with it. Yeah. Okay. A couple of examples. So, if you know a linear transformation and you want to ask how do you represent that linear transformation as a matrix, we talked about that with the last example. This sort of goes the other way. Suppose you don't know the linear transformation, but you know how to represent it with a matrix. What does that tell you about the linear transformation itself? Well, so keep in mind, as we've discussed, these numbers, for example, are telling you that we're taking the first input basis vector, we're applying t to it, and then we're writing the results in W language. Right? So this first column here, 1, 0, 1, that's the W coordinates of t of v1. And so keep in mind, this equation is identical to that equation. Right? This that I have circled down below here, this is the definition of what that means. If you have, a vector's coordinates with respect to a basis are certain numbers, that means that vector is that linear combination of those basis vectors. And this gives you kind of what you're looking at. This tells you something about t. T does this to the vector v1. And then likewise for the other columns, in the same way that that column tells you these coordinates, or these coefficients, likewise that column tells you about the image of W2, and that column tells you about the image of W3, all, of course, in W coordinates. Okay. This next example is identical. It's really, really very similar. So I'm just going to let y'all read this example. It's morally equivalent. Here's a matrix. What can you conclude about the transformation? There's something about this example that will be of particular interest a little bit later on. So I'm going to call back to this example later. But anyway, read through it. It's, like I say, identical to the one above. Okay, good stopping point. See y'all later. Have a good day. Oh, don't forget, of course, exam on a Wednesday. And don't forget to put in the attendance code right there. Okay, see y'all later.